Welcome to the SPI chapter of the HT32 MCU basic tutorial. Here is an introduction to the chapters in this tutorial. What is SPI? Overview of SPI Protocol. SPI Features and Functions. SPI Example. And SPI API List. What is SPI? What is SPI? SPI stands for Serial Peripheral Interface. It is a synchronous serial communication interface that allows data communication on 4 pins. It is a high-speed, full duplex serial data transfer interface. It operates in a master or slave mode, usually having one master device and one or more slave devices. Overview of SPI Protocol. Then we will start to take an overview of the SPI Protocol. The SPI interface uses 4 pins, among which are the slave select line SEL, the clock line SEK, serial data input and output lines MISO and MOSI. SEL stands for slave select signal. It is controlled by the master and is used to select the communication target. Information on whether data transfer is valid or not is provided to the slave by the SEL level. SCK stands for serial clock signal. It is a synchronization clock signal provided by the master to the slave. The master and the slave need to perform data sampling or data latching according to transitions on the SCK signal. The SCK indicates the SPI transmission rate. MOSI stands for master output slave input. It is controlled by the master and is used to transmit data to the slave. MISO stands for master input slave output. It is controlled by the slave and is used to transmit data to the master. The overall SPI communication diagram is shown below. SEL is controlled by the master. When receiving a communication or about to communicate, pull the SEL pin low or high to select the target slave to inform it to communicate. SCK is provided by the master, outputting a synchronization clock signal. The master uses MOSI to transmit data to the slave for reception. The slave uses MISO to transmit data to the master for reception. Now that we have learned about the basics of SPI, we will move on to the SPI serial frame format. Firstly, we will introduce 2 bits, the clock polarity bit, CPOL, and the clock phase bit, CPHA. CPOL is used to set the SCK clock polarity. When the clock polarity bit is cleared to 0, the SCK line idle state is low. When the clock polarity bit is set to 1, the SCK line idle state is high. CPHA is used to determine where the data is sampled. When the clock phase bit is cleared to 0, the data is sampled on the first SCK clock transition. When the clock phase bit is set to 1, the data is sampled on the second SCK clock transition. 4 different formats can be generated by setting the CPOL and CPHA bits. The timing diagram for single byte transfer in the 4 SPI modes is shown below. In the mode 0, CPOL is equal to 0 and CPHA is equal to 0. The SCK line idle state is low. The data is sampled on the first SCK clock transition. In the mode 1, CPOL is equal to 0, CPHA is equal to 1. The SCK line idle state is low. The data is sampled on the second SCK clock transition. In the mode 2, CPOL is equal to 1, CPHA is equal to 0. The SCK line idle state is high. The data is sampled on the first SCK clock transition. In the mode 3, CPOL is equal to 1, CPHA is equal to 1. The SCK line idle state is high. The data is sampled on the second SCK clock transition. SPI Features and Functions. Then we will take the HT32F52352 as an example to introduce the HT32 MCU SPI Features and Functions. Supports master or slave mode. The frequency is up to FPCLK half for the master mode and FPCLK third for the slave mode. Programmable data length of up to 16 bits, from 1 to 16 bits, with an 8-level FIFO. The transmission can be either MSB or LSB. Programmable slave select active polarity, high or low active. Support multi-master and multi-slave operation. Master mode supports the dual output read mode of SPI series NOR flash. For error flags with individual interrupt, read overrun, write collision, mode fault, slave abort. Supports PDMA. As shown in the table, there are several flags with individual interrupt. TX and RX related flags are the TX buffer empty, TXBE, the transmission register empty, TXE, and the RX buffer not empty, RXBNE. The timeout flag is only available in the FIFO mode. The timeout counter will start counting and be used as a timeout mechanism if the SPI RX FIFO is not empty. The mode fault flag can be used to detect SPI bus usage in the SPI multi-master mode. The SPI multi-master mode is shown in the figure. There are more than one SPI master. The mode fault detection is required depending on the situation. Trigger conditions are shown below. The SPI is in the master mode. SEL pin is configured to be the input mode. SEL signal changes to an active level when driven by the external SPI master. At this time, the mode fault flag is set, the SPI interface is disabled, and the mode bit is reset to force the device into slave mode. In the non-FIFO mode, the write collision flag is asserted to indicate that both the TX buffer and the shift register are already full. In the FIFO mode, the write collision flag is asserted to indicate that both the TX FIFO and the TX shift register are already full. Any new data to be written will be lost. In the non-FIFO mode, the read overrun flag is asserted to indicate that both the RX shift register and the RX buffer are already full. In the FIFO mode, the read overrun flag is set to indicate that the RX shift register and the RX FIFO are both full. This means that the latest received data cannot be shifted into the SPI shift register. As a result, the latest received data will be lost. In the SPI slave mode, the slave abort flag is set to indicate that the SEL pin suddenly changed to an inactive state during data transfer. Then introduce the SPI master SEL pin status and PDMA interface. The SPI master SEL pin status can be divided into two types, input and output. This is set by the SELOEN bit. When SEL pin is set as an input, the SPI supports multi-master. Use another GPIO to replace the SEL pin function. In the continuous transfer, case 1 does not support, case 2 supports. When SEL pin is set as an output, the SPI does not support multi-master. Using SELM setting can set the SEL pin to be controlled by hardware or software. In the continuous transfer, case 1 only supports hardware control, case 2 supports hardware or software control. The SPI PDMA interface can be enabled by setting the TXDMAE or RXDMAE bit to 1 in the transmitter or receiver mode respectively. When the TXDMAE bit is set to 1 and the TXBE flag is asserted, the PDMA function will be activated to move data from the memory location that users designated into the SPI data register or the TX FIFO until the TXBE flag is cleared to 0. When the RxDMAE bit is set to 1 and the RxBE flag is asserted, the PDMA function will be activated to move data from the SPI data register or the Rx FIFO to the memory location that users designated until the RxBNE flag is cleared to 0. The TXBE flag will be asserted when the transmit buffer is empty in the non-FIFO mode or the data contained in the TX FIFO is equal to or less than the level defined by the TXFTLS field in the FIFO mode. The RxBNE flag will be asserted when the receive buffer is not empty in the non-FIFO mode or the data contained in the Rx FIFO is equal to or greater than the level defined by the RxFTLS field in the FIFO mode. Finally, let's look at the SPI dual mode. The SPI dual mode is only used in the master mode. A more efficient data transfer can then be implemented by using this dual mode together with the 4 formats described above. Note that, in the dual mode, the SPI data transfer only supports input direction, that is, reading data from external devices. The MOSI pin changes the direction from output to input, using with the MISO pin to read data synchronously. This mode supports a data length of 16 bits. Note that the DFL field should be set to hex 8. The figure shows the SPI dual mode timing diagram in the SPI mode 0. As shown in the figure, the MOSI pin changes the direction from output to input, using with the MISO pin to read data synchronously. The data length is 16-bit. SPI Example. Next, we will use the firmware library SPI Example, FIFO SEL hardware, to briefly introduce the SPI application method. The hardware will use the HT32F52352 to illustrate I/O and SPI usage examples to summarize this tutorial. The example flow is shown in the figure. Firstly, initialize the DVB LED for displaying the final data comparison result. Then configure the SPI, including the master and the slave. This example uses 2 SPI IPs. Finally, transfer and data comparison are performed through the SPI loopback. If the transmitted and received data are the same, LED 1 lights up. If they are different, LED 2 lights up. The following will introduce the example of an SPI configuration setting. The content will be presented using the SPI-related pins or IPs defined in the HT32F52352. Actual usage should be based on the HT32 MCU device and the I/O alternate function table selected by the user. Enable peripheral clock, including SPI 0, SPI 1, AFIO and master SEL port. Configure SPI I/O and switch to the SPI function. SPI configuration, including the master mode and the slave mode. Set SEL as output mode. Enable the SPI RxBNE, TOUT interrupt and nested vectored interrupt controller. Set the timeout counter. Enable the SPI slave first and enable the SPI master later. SPI API List. This tutorial concludes with a list of the SPI API, including the SPI driver API provided by the HT32 standard firmware library, along with their corresponding descriptions. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.